Hello everyone. So we are from group 9, 10 and 12. We are going to present about derivative-free optimization. And then our group members are Mohammed MAHFUZUR RAHMAN, RIDWAN bin MONJUR, RAQIBUL Islam, CASSANDRA MING, Yang DONGDAO, SHAIDAH Binti ISMAIL, Mohammed Dannyel, Elysia Maida Joanda, Fadila utami, and Laila Nabilah. Okay, so derivative-free optimization is a discipline in mathematical optimization that does not use derivative information in the classical sense to find optimal solution. It cannot be derived and use evolutionary concepts. It also addresses the problem of optimizing over simulation where a closed form of the objective function is not available. The development in the theory of derivative-free optimization algorithm have made them useful for many practical applications. However, most of the existing derivative-free optimization algorithms do not show satisfactory performance on high-dimensional problems. Derivative-free optimization is useful at finding local optimal for continuous domain smooth single model problems. Various methods can be employed to address these challenges using only function value of f. Some method can discover the optimal, but some rather meta-heuristic since the problems are in general more difficult to solve compared to convex optimization. So next, I'm going to pass to my group member for the characteristic of the FO technique.
Okay, after you know the definition of the derivative-free optimization that Laila explained, so I will explain about the characteristic of the derivative-free optimization. So what is the characteristic? So the first is derivative freeness. It means that does not require derivative and rely on the repeated evaluation of the objective function. And then the second is intuitive guidelines. Guidelines based on the simple intuitions. Some concepts are based on the nature, wisdom, and thermodynamics. And then the slowness, it meaning that the comparatively slower to derivative-based optimization techniques. Next. And then it's about the flexibility, meaning that it works well with the complex objective function, and also about the randomness is about the derivative-free method are stochastic in nature, meaning that they are global optimizers given enough computational times. And then the last thing is about the analytic opacity. It's meaning that the difficult to do analytic studies of this method. Most of the knowledge about this method are empirical in nature. And next. And then why derivative-free optimization is established? So here is the list of the reason. First is growing sophistication of the computer hardware and mathematical algorithm and software, which is open new possibilities for the optimization. And then the second is about the function evaluation costly and noisy. So, and then next one is about the binary code, source code not available or owned by a company, meaning that making automatic is the differentiation impossible to apply. And then it's about legacy codes. And the last thing is about the lack of sophistication of the user.
In order to understand the derivative-free optimization algorithm better, we'd have to look into related calculation. But before we dive into the calculation, we'd have to note that the derivative-free optimization algorithm actually includes a wide variety of different methods, including the Bayesian optimization, genetic algorithms, nail-the-meat method, particle sum optimization, pattern search, random search, simulated annealing, subgradient method, and some other methods that are not enlisted in the slide. However, in this discussion, we're going to just look into the calculation for the widely applied algorithms, such as the nail-the-meat method, the genetic algorithms, and also particle sum optimization. So first of all, we're going to look into the calculation for nail-the-meat method. This method is a heuristic search method, which is going to converge to a non-stationary point, and it is a downhill simplex method, which is a simplex method that is searching for the minimum solution. And it is using the concept of a special polynomial with n+1 vertex in n dimensions. For example, if we involve a 2D dimensional space, so it's going to involve 3 vertices, which is a triangle on a 2D plan. And for this method to work, it involves a simplex transformation controlled by reflection, contraction, expansion, and also shrinkage. So next, we'll be looking into this animation, which is an animation that is demonstrating on how nail the meat method works. You can see that on this 2D solution space, we establish a triangle on the space, and by reflecting, shrinking, expanding, and contracting itself, this triangle eventually converges to the optimal solution. Next, we're going to look into the steps for the iteration of the nail the meat method. First of all, we're going to discuss in the 2D space, we're going to order the 3 vertices here from the worst, second worst to the best vertices. So when we talk about a worst vertex, it is the vertex with the highest cost. Next, we'll be checking out the centroid. For the centroid, it is the midpoint of the line oppositing the worst vertex. We can see that from the figure as shown at the side. And the next thing we want to do is to perform the transformation on the worst vertex. The transformation includes reflection, expansion, shrinkage, and outside or inside contraction. So let's check out the flow chart in order to perform the nail the meat method. First thing first, as mentioned just now, we're going to order the vertexes according to the cost function in ascending order. Next, we're going to calculate the centroid based on the worst vertex, and we're going to find out the midpoint of the line oppositing the worst vertex. And after having the centroid, we're going to perform the reflection on the worst vertex. After reflecting, we'll be performing expansion on the vertex to check if we can achieve a better solution. If expansion doesn't work, we'll move on to contracting the vertex. And if contraction gives a better solution, that would be a new solution. And if not, we're going to try for shrinkage until we achieve a better solution than the worst vertex. And we'll keep on repeating all these processes until the triangle finally converges to a point. So that's all for the nail the meat method. And next, I'll pass it to the next team member.
This part, I will introduce genetic algorithm. Genetic algorithm, one of the derivative-free optimization algorithm. It is a method for solving both construct and unconstruct optimization problems that is based on the nature's lessons. The procedure that tracks biological evolution. The genetic algorithm modifies a population of individual solutions at each stage. The genetic algorithm selects individuals from the current population to be the parents and use them to produce the children for the next generation. Over the 6th generation, the population evolved toward an optimized solution. The picture shows the step of the genetic algorithm. Okay, next. And how it worked. Here is the detail. First, create a random initial population, and the second, create a sequence of the new population. At each stage, the algorithms use the individual in the current generation to create the next population. Here is the detail of the algorithm. Score each member of the current population by computing its fitness value. These values are called the raw fitness score. Scaling the raw fitness score to convert them into a more useful range of values. These scale values are called expectation values. Select members called parents based on their expectation. Okay, next. Some of the individuals in the current population that has low fitness are trained as elite. These elite individuals are passed into the next generation. Produce children from the parents. Children are produced either by making random changes to a single parent's mutation or by combining the vector entities of a pair of parents crossover. And finally, repeat the current population with the children of the form, the generation. This is the step of the create a new generation. And the next is the algorithm stores. When one of the stored criteria is missed, the algorithm takes modifies this for linear and integer constraint. The algorithm is further modified for the non-linear constraint. Okay, that's all for the genetic algorithm. So next to my group members.
Okay, so I will proceed with the third derivative-free optimization algorithm, which is particle swarm optimization, PSO. So PSO is a stochastic optimization technique based on the movement and intelligence of swarms. So it uses a number of particles that constitute a swarm moving around in the search space, looking for the best solution. Position and velocity are influenced by each particle's best known position, which is also updated by better position found by other particles in each iteration. So PSO is applied widespread in optimization due to its global search ability and fast converge speed. So next slide. Okay, so here is the list step for PSO algorithm. Well, the first step is to create a population of agents, which is uniformly distributed over S. And then the second step is to evaluate each particle's position, considering the objective function. And the next steps, if a particle's present position is better than its previous best position, then we need to update it. And followed by finding the best particle according to the particle last best places. And then update the particle velocity using the formula shows in the slide, where VI stands for the velocity of the particle, C1 as a cognitive constant, C2 as social constant, W initial weight, and U1, U2 represent as random numbers, PB as a personal best, GB as global best, and PI represents as a position of the particle. So next slide. To move particles to their new position based on the formula stated. And last but not least, go to step number 2 until the stopping criteria are satisfied. So next slide. Okay, basically this is the analysis of the particle swarm optimization algorithm, where the first equation stands for the initial, as it makes the particle move in the same direction and with the same velocity. And the second equation represents as personal influence, where it makes the particle return to a previous position better than current. And the last equation represents as social influence, which makes the particle follow the best neighbor direction. So that's all from me. I will pass to the next presenter. Thank you.
Okay, now let's move on to the examples. The first example is ASA, which stands for Adaptive Simulated Annealing. It is a derivative-free software resolver, and it is implemented using the programming language C, which is used to develop for unconstrained optimization problems. ASA differs from the traditional simulated annealing in that it involves generating probability density function, which flatter tails that a typical Boltzmann distribution. It also allows an ASA to possibly escape from the minimum or local minima by considering points far away from the current iterate. Separate temperatures parameters are assigned for each variables, and they are updated as the optimization progresses. Now, for the next example, I would ask Raqib to present.
Okay, thank you, MAHFUZUR. So the second example would be the Dakota solvers. The full form of Dakota is Design Analysis Kit for Optimization and Terrestrial Application, which is a project at Sandia National Laboratories. Dakota's initial scope was to create a toolkit of black box optimization methods. The scope was later expanded to include additional optimization methods and other engineering applications, including design of experiments and non-linear least squares. Dakota contains a collection of optimization software packages featuring the Colony library. So next, RIDWAN will explain the third example.
Third example is BOBYQA, Bobby QA. The bound optimization by quadratic approximation. Bobby QA is a Fortran implementation of Powell's model-based algorithm. The purpose of Bobby QA is to minimize the function of many variables by a trust region method that performs quadratic models by interpolation. Bobby QA is an extension of the new ULA algorithm to bounded problems with additional considerations on the set of rules that maintain the set of interpolating points. So now I pass to my next teammate.
Okay, now I'm going to explain about one of the example of the coding. For my example, I use the particle swarm optimization method. So here is the parameter of the input, and then the hyperparameter, which is the number of particle, the iteration, the population, set the initial coefficient, cognitive coefficient, and social coefficient, and then that's the detail of the input. Next. Okay, first we input the library, and then we're gonna do REST region and sphere function. So we set up fitness function for REST region and sphere function. Next. Then we do the set up the particle class for PSO. We define initial position and initial velocity, and then we do the code for the computing the fitness of the particle, and then we set up the code for initialize best position for fitness of the particle. Next. So for the particle swarm optimization function, we define with W, C1 and C2. And then we use a random using this random number is using the pseudo method. And then we create a random particle from the code. And then we compute, we set up the code to compute the best position. And then we set up the code to compute best particle and swarm and its fitness. Next. So this is the main loop of PSO. The left one is for sorry. Okay, this is when we do the iteration, the optimization. So we can see this is the drive coding. The left one is we set up the random number, and then we run velocity. We set up the velocity, and then we compute new position using the new velocity, and then we compute fitness of new position, and then we find out which position is best for the particle, and then last part we try to find what's the best position for overall. Then next. So this is the driver for the REST region and sphere function, the code for the drive. Next. Okay, so here is the output. The left side we can observe REST region. When we run the optimization, the best solution found is at 0.00618, 0.00013, and 0.00616. And the best solution is at 0.00151. So from the iteration function, it is between 50 to 60 iteration. If we use when we use the sphere function, so the best solution, we can find the 3 coordinate, and the fitness of best solution is at 0.00. So we can conclude that with the sphere function, the optimization is at iteration between 40 to 90. Okay, that's all from me. I pass for the next coding example.
Okay, this is an example of coding from genetic algorithm, and this data is run using a Google Colab. Next. After follow 6 step in genetic algorithm. Next. 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 This is a problem definition that we get from the data. And next. Okay, so it can be concluded that number of iteration to be run depend on the nature of problem. In this example, we are running 53 iteration. So the value reduced to 2.15. Consequently, giving us the optimal solution. Okay. Next. This is a reference from our group that